Hi, I'm Weixing. I work for research at Comma. Today I'm going to talk about how we view driving with openpilot as a human-machine cooperation problem and how we use machine learning to improve things. So this is how we drive without openpilot as a human. Basically, the driver is the only actor here. But with openpilot, the driver's role slightly changes, and they will now work cohesively with openpilot, with the driving model specifically in some way. So today's talk will be focusing on different aspects of the dynamics between the human and the driving model shown in this graph. So we will cover how we use the power of machine learning to learn about the driver, and then learn about the driving model, and how we ship many impactful improvements along the way. As we know, openpilot as a driving assistance system requires the user to be able to take over at all times. In simple words, you need to pay attention. We already covered how driver monitoring works in openpilot from the last Comic-Con talk 2 years ago. So today we'll be focused on the progress we made since that time. So this is what the driver-facing camera looks like on the old Comma 2. It's a bit noisy, but mostly it only shows a limited view of the interior for the driver due to a very small view on the Comma 2. To make things worse, due to limited compute on the Comma 2, we had to crop the image and feed it into the model. It's not fun to build a DM like on inputs like this, trust me. For the model, it was like watching a movie, like with all the people standing in front of you, like blocking the view. That's basically how it felt like. Moving to the Comma 3, this is the initial model we shipped using the Comma 2 data before we had any real amount of Comma 3 data to train on. And this is the new model we train on the new Comma 3 data. And the model we ship currently is shown. It's shown with the green box, which basically covers the whole interior instead of just some part of the driver. Now, as we can see the full body of the driver and hand and even the steering wheel. And then the same is true for also the passenger. With that, now we have achieved on the Comma 3 almost 100% of face detection rate. With that, we can remove the wheel touch when the camera is not blocked and use vision only for DM. Yeah, because it's not the best idea to assume the driver is paying attention when they are touching the wheel, because that can easily be cheated, like in a Tesla. So another thing we can do was to remove the right-hand drive toggle, with the model now being able to detect whether which side the driver is driving on. Say you're in like the US, you're on the right in this image, or you're on the other side if you're driving on the wrong side of the road. So with that, we can remove the right-hand drive toggle. One less toggle is always better, as Adib says. We'll come back to that passenger thing a little bit later. So in terms of true positive, we have achieved a net gain of almost 2x in true positives by using a bigger model box. And then now we also have the extra benefit of the extra context we have with the full interior camera. With the extra context, we are able to build upon it to do this. So last time on my Comic-Con presentation, I mentioned that we will explore moving to a more end-to-end approach, a more end-to-end approach for DM. Now I think it's a good time to do that. So in a classic DM policy, we have the model that predicts some attributes of the driver, and then those are fed into some state machine to determine whether the driver is distracted. But in an end-to-end DM world, the model should be able to tell from the footage, like whether the driver is paying attention or not directly. So here is an example of a deep driving. As you can see, other than when he was looking right at the road, or when he was like straight distracted by his phone. There's also a lot of gray areas there. As a human, even as a human, it's tough to tell like whether sometimes he's paying attention or not. So we need to define attention to be able to like have good ground truth for end-to-end DM to learn from. Here's a hint. DM doesn't live in a vacuum. It's part of the system, part of the openpilot system. So what is attention really? So the answer really is quite simple. We already know that openpilot as a driving assistance system again. The driver should always be ready to take control. So with that in mind, we are ready to get our ground truth. With that in mind, it's simple that the paying attention definition should be whether the driver is ready to take control at any time. With that in mind, we're ready to get our ground truth for the end-to-end DM system. So we make two simple assumptions. The first one is the probability of taking control is higher when the driver is driving or taking control. That's pretty obvious. And the second one is the probability of not taking control is higher when the car is at a standstill. So it turns out we already have those things in the logs for a long time. Therefore, you can just use them to train the model to predict from the driver footage whether the driver is ready to take control or not. So with those naive ground truth I just mentioned, we train a vanilla end-to-end model that predicts whether the driver is distracted from some frames. And you can see that it sometimes reliably detects when the driver is really distracted, like he was looking out the window. He was definitely not ready to take control here. But the model also thinks that he was not ready to take control here, where he was just chill driving. And so it's this. He was looking at the road while turning the radio, which in a taking control context is fine. So we need to fix those false positives. So we realized that the only way to fix all the ambiguity, which it's most likely a finite set, is to have the real human to label some of those difficult scene cases. Because of the fact that we already have a helper model that's trained on vanilla DM labels, we can use that model to help us find all the interesting stuff. And then only 2% of our entire data set ends up needing to be labeled. To get the perspective, we outsourced the labeling work to a third party, and it took them only one person in less than 3 days to do our labeling. We pay virtually nothing to gain a lot of improvements in our ground truth. So with that improved ground truth and our end-to-end DM model trained on that, the model is now able to pick up additional subtle distractions like using phone without force triggering on chill driving poses, like in this example, in this example shown here. Whenever the timer drops, it means the system thinks Adib was distracted. So you can see this is fairly accurate because when the timer drops is where Adib was really not able to be ready to take control. So to put it in a number, we have metrics showing that the net result of adding end-to-end policy is to have a 15% gain in true positive with no false positive gain. So now let's change our focus onto the driver by looking at some behavioral metrics. Remember in full-frame DM I mentioned earlier, we are now able to detect from DM model if there's a passenger or not. So by overlaying that with the driving data, we came to the surprising conclusion that when people drive alone compared to driving with passenger, they are 4 times more likely to take a corner over half a G. And 2.5 times more likely in hard braking. And twice more likely to tailgate someone. So that all that aggressiveness difference in driving from having a passenger or not inspire us to do a whole driving style analysis on our fleet. We basically classify driving style using metrics like hard braking, hard acceleration, or like hard turning, etc. And then those things are used as a conditioner to fit into the driving model. And as Harold mentioned, by using like the chil profile, we actually make Taco Bell drive much easier by making it drive smoother. So another metrics that is super important to our company is that we need to understand the relation between making driving chill and potentially making drivers more prone to distractions. As always, we talk with numbers, and we have metrics for exactly that. So the first conclusion from our metrics is that drivers generally pay more attention to the road when using openpilot than not using openpilot. So here, the green curve shows the distribution of segments with different percentage of distracted times when engaged with openpilot in green, or not engaged with openpilot in red. So essentially, the more left the curve, the less distracted the drivers are. So we can see that when engaged, drivers are generally less distracted. That number actually is around 40%. So that's a big improvement. So actually, it's actually not too surprising to imagine these things, because with openpilot, it first takes away the taxing stuff from driving and allows you to pay more attention to the surroundings. And also, it's hard to not pay attention when it yells at you when you get distracted. The second one is actually more interesting. There's a common doubt that if you've been using openpilot for a long time, you start to lose attention and become complacent, and in the long run. But our long run metrics disagrees with that. This is an aggregate of the same bunch of drivers in the long term. Distraction trends, and the lines remain pretty flat for different percentiles of distraction durations. So we are confident that our users don't get more distracted as time goes by. So now with the driver out of the way, let's talk a little about the driving model itself. So the model is an integral part of our human-machine system. And it's crucial that we understand how the driver can interact with it and how it can potentially interact back with the driver and make the experience more coherent. The human driver mostly interacts with the driving model by disengaging or overriding. Those disengagements give us strong signals of when and hopefully why the model doesn't do well. And therefore, we've been putting a lot of effort into building and looking into disengagement metrics. We've been tracking the longest time openpilot can be engaged, which is easily in the hours. It's good to know openpilot works, but this kind of stuff all look like this, and it can't really help us improve. It's like similar to someone who learned driving on the highway only, and they can't really learn anything. So the question we have been asking lately a lot is, where do openpilot users tend to take over? And we build this. This is our automatic disengagement reports. So it's a tool that enables us to do large-scale, up-to-date disengagement analysis. So it runs daily, automatically, and it's shown on our biggest TV in research. Essentially, it gathers all the lateral and longitudinal override data, as well as the unexpected disengagements. And then with all the logs parsed, we are able to group all the disengagements by the disagreements between the human and the model, so that we can split them into different classes as shown here. And here are just some examples of different kinds of disengagements. So basically, we show a list of random examples for each kind of disengagements on the reports. And then everything is visualized with necessary data. Like in the GIFs here, we can see in this report, there's been turn cutting, and we can like go to the turn cutting person in comma, which is one person, and say turn cutting team, which is one person, and say, oh, there's been a lot of cutting lately. What's going on? And then hopefully we can have it fixed. So here is another example of how we use this report to fix a real complaint. So there's been, as people know, like there's a lot of noise about people asking, oh, we need to adjust the following distance. It's following too far on the highway sometimes, like this Discord user, Johnson. And yeah, we listen to that, but we need to back that up with data. So we look at the disengagement reports, and we saw this. There's like, so you can see there's more than 30% of our longitudinal disengagements is due to the model following too close or it's braking too hard, too early for a lead car. So we know that this is a real problem. And then by like giving this to the right person, we were able to figure out not only this is a real problem, but also we know how much we need to fix this problem. So we come up with the latest longitudinal personality toggle in our settings. So the last point I want to discuss is how the driving model can potentially give feedback back to the driver to communicate his uncertainty. So first of all, how do we know if the model is uncertain for some given scene? So well, we can try to ask the model itself, since we already have the model output some disengagement predictions for a given amount of seconds in the future. So actually here we have metrics that compares the actual disengagement numbers versus the model predictions, and we can confidently say that they match pretty well. So we can rely on the model itself to tell whether it's certain or not. Here is a spectrum of scenes that the model is feeling different degrees of confidence. On the left, we have the boring stuff. It's just like straight, long highway roads. And in the middle, we have traffic and some interesting country roads, and maybe sitting behind an NYPD car at a traffic light, which makes the model more uncertain. And on the right side, we have like things where scenes where openpilot would probably not work, like merging this UK narrow road or turning onto this busy street after a stop sign. So the first step we can do is to show uncertainty in some kind of confidence indicator in UI. This is actually a work in progress we're doing now. So remember that in 094, we shipped the always on border, which means it always communicates the engagement status. So we're thinking, why not? We can use that and change that to something less green when the model is less confident. So say in this example, here it's just like one lane road, it drives fine. But here, then like 2 seconds later, it sees this potential divergence, and it becomes less confident and might might need your attention. So it's nice to have that dynamic between the model and the driver. And also, like, say, when the bird finally poops on your car, it probably becomes red. So, yeah, that was my talk.
All right.
Hey, great talk. Couple of questions for you. What's your overall thought on the long-term time and investment that's going to be spent with DM as we actually every day get closer and closer to level 4, level 5, where conceivably you don't care that if the driver's asleep or in the back seat completely. What's your general thought on that? How that's going to evolve?
I mean, in the context of openpilot, we probably always require the user to pay attention. But in terms of level 4, level 5, I would say there will be in the future some interplay between like how confident the model feels and how the DM policy should adapt. I think that's the final goal.
Okay, that makes sense. So maybe certain times it might be needed, but other times it would be fine and maybe alert the user to, hey, we need you to probably pay attention now to be safer, but in general, you're okay otherwise.
Yeah, we already have some adaptive DM policy in place, so that may be a good place to start.
Okay, and then just a quick question on the actual eye gaze and tracking on that.
Yes.
I know with like Teslas, you can just put on sunglasses and it says, yeah, he's paying attention, even though your eyes can be completely closed. Does this system have anything with like eyewear or glasses that, you know, that it's not detecting eyes, and does it assume that you're fine? I don't know if it's common knowledge of how that works or not.
I think whenever your eyes is invisible, it just falls back to a head pose. And the end-to-end policy is actually really good that when you have some weird poses, other than just normal driving position, say you're sleeping when you're wearing sunglasses, it can probably pick that up and say, oh, there's an anomaly here.
Great. I got a question here in the back.
Hello, awesome talk. Do you think that near symbolic approach with something like prepositional logic will be viable solution for deeper understanding of actors in environment?
Sorry, can you repeat?
Do you think that in future near symbolic approach with formal logic, declarative logic with sub-symbolic models will be viable to deeper understand the behavior of actors in environment to predict future?
I'm not sure about symbolic.
Near symbolic, it's like deep learning plus declarative logic.
Oh, I see. I mean, our end goal is to have end-to-end driving model that just looks at the scene and tells us where to drive and potentially like how confident it is about like doing this path. And I think in the future, as the driving model gets better, it should just be able to tell like naturally with our end-to-end approach. Does that make sense?
I wonder if you could share a little bit about how you classify and what breakdowns of data you get from classifying drivers as chill or not. It's a fascinating topic for me. I've gotten old and I use openpilot a lot, so I mostly drive chill, but every once in a while I throw my car on an autocross course and I use openpilot as a data logger. So is there a memory to that? Are you classifying per segment, per route, per device? And
it's a per route.
As a off-the-wall question, how many openpilot users would you say are good drivers?
I mean, we classify them into 5 categories, basically. But I don't think we track like specific dongle IDs. We more like focus on the route, I believe. Yeah.
Got anything else, Weixing? That was a lengthy question. You satisfied with the answer, Jason?
You kind of dodged the one where I asked how many openpilot users were good drivers.
Will we opt in to share this with your insurance company?
All right, we got a question upstairs.
Question. Thank you. If you come back to like 2 slides back, in terms of like giving feedback to the customer about uncertainties, communicating, I'm thinking if it's possible at all, but yeah, not exactly that, but where you had like uncertain model being uncertain about specific and trying to communicate it back to the driver.
Sorry.
Not this one, like the real like mock-up of the road, like with the vehicle, like the picture, like few more slides,
A few more?
maybe like forward, not back.
Oh,
No,
the
no.
one with the driving behavior?
Yeah.
Here?
No. There's one of the last ones, like.
Which one?
The red and the yellow one.
Oh, this one. Oh, wait.
No, with the road, like. With
Oh,
the
sorry.
pictures.
Yeah, sorry. So, this one.
No, more. No, you're going to the right direction, but to the end of the presentation.
Yellow, the forward-looking statement.
Oh, that. Sorry. That's too
Yeah, this
forward-looking.
one.
I almost forgot.
I'm thinking, I don't know if it's possible at all, but it would be nice if it could also communicate some areas where it does not want to go, like for example, if there is like vehicle parked or like some blockage or whatever. So like maybe in like I don't know in the red.
Yeah, we can have a hard cutoff, like ideally for like some sketchiness of the scene, and say, oh, you should probably disengage here, and give you a super short timeout.
Anyway,
If that makes sense.
yeah, cool stuff. Thank
Yeah.
you.
All right, I'm coming over here.
Hey, awesome talk. You mentioned you make some assumptions to determine whether the driver is attentive.
Yeah.
Like if they're driving, they could be more attentive. If they're at a stop, maybe less attentive. So I was wondering, like, I assume these are neither conclusive nor do they always hold. So in the future, do you think it's possible to also use data from the driving model? Like maybe if someone's drifting out of the lane or if they stop more suddenly than the model was, do you think that can be used as a negative signal for the driver monitoring?
Do you mean when engaged or not?
I guess either way.
Either way. Yeah, I think that stuff is a little bit more far away from like what we're looking for. Because in here, although those things might not seem immediately obvious, you can see in the data there's a distribution shift from, say, taking control or not, or like being standstill or not. And we picked up that signal and we capitalize on that to determine whether the driver is ready to take over. I think that's good enough with some refinement.
I have like a kind of a far-fetched question, but have you ever considered using driver monitoring to not just communicate like uncertainty between the model and the human, but somehow have the human communicate intent back to the driving model? For example, during a lane change, if the human is looking in the rearview mirror, you could use that as a signal that the human wants to is affirmative, that it knows it can turn left.
Yeah, but we cannot always assume that. There will be a lot of false positives, so whichever way.
All right, we got
It's an
time
interesting
for
point.
one last question.
Do you measure the driver takeover or disengagement reaction time somehow? Like when model is openpilot is driving for 2 hours, and do you see that it affects driver's reaction time in case he needs to disengage?
What's the question again?
Do you measure somehow the driver's reaction time? Does it change if the openpilot has been driving for example, 2 or 3 hours without disengagements?
You mean the DM threshold, timeouts, or the model confidence slash disengagements?
If there is an if there's an
That. We don't have metrics for that. But I think like the second long-term DM metric is pretty conclusive about like people using openpilot for a long time.
Okay, thank you.
All right, actually, we got one more question. Someone over here have a question? We good? All right. Thank you so much, Weixing.
Thank you.